So I'm going to put you to work right away in this lesson here. I want you to try to figure this out on your own. I'm not just going to tell you. I want you to try to figure out, what does a log function graph look like? No cheating, no calculators. Don't use those graphing calculators. Don't use Desmos. No cheating. I want you to try to figure this out on your own. I want you to try to graph y equals log base 2 of x as best as you can. Try to figure out on your own, what does that graph look like? Can you figure out at least part of it all on your own? If you're stuck, if you're not sure where to start, of course, anything that we're not sure how to graph, we can always go back to making a table. Just plugging in points, figuring out some nice numbers that would give us some nice points on the graph. So go ahead and give that a try. Try to do at least a few numbers in that table, plug in a few numbers, try to find a few nice points for the graph. So this is where most people usually start. This is the part of the graph that most people can usually figure out on their own. They can't take log of a negative number, can't take log of 0. There's no exponent you can put on a positive number to get either -1 or 0. But we can have some of these positive whole numbers here. These powers of 2 give us some nice points on the graph for the log function. And so this is what a lot of people usually come up with at first. It's not the whole graph, though. It's missing a little bit. Notice that I left some space here between 0 and 1. There's actually a whole lot of numbers between 0 and 1, right? Some of those numbers will give you some nice points on this graph here. So if this was your whole graph, take another minute or two, see if you can find some more points. See if you can figure out the rest of the graph, thinking about some values of x between 0 and 1. This is what the graph, the full graph, should look like here now. So we actually have a vertical asymptote. So what happens is, again, we've got these numbers between 0 and 1, these fractions for negative exponents. So we can have negative y values. So something that could have been helpful here is, if you looked at this, if you changed forms here, if y equals log base 2 of x, then that means 2 to the y equals x. So you can try different exponents for y to figure out the x value. Normally we plug in x and figure out y, right? Here you could have actually started with y values, and it could have given you x values. So these negative y values give you fraction values for x. And so, of course, the more negative that y gets, the closer to 0 x gets. We can't have x actually equaling 0, but we can have x getting closer and closer and closer to 0, as close to 0 as we want. So we get this vertical asymptote here, getting closer and closer and closer, but never quite touching the y-axis. Okay, so that's the full graph of a log function. So we figured it out now, thinking about just making a table. We also could have figured it out by comparing it with the exponential function. Okay, so let me remind you of what the exponential function looks like. You think of, e to the x, 5 to the x, 2 to the x, something like that. We had one nice point on the graph. See if you remember what that nice point on the graph was. It was a y-intercept, the point 0, 1, right? Any number to the 0 power gives us 1. So regardless of what the base was, we always had that y-intercept of 0, 1. And then when we're an exponential function, when x is negative, those negative exponents made fractions and made us get closer and closer to 0. And so we had this horizontal asymptote right there. When x got bigger, the graph shot up like that. Okay, so this was an exponential function. The domain x could have been anything. The range, we couldn't quite have 0. So the range, we had parentheses 0 going to infinity. Okay. Well, let's try to compare this exponential function with the log function here. What if I changed this to log form? Well, this would be log base b. Logs are exponents, so this would equal x. And then I would have y right there. Compare that with this log function that we're trying to graph. What happened? We switched x and y, right? We switched the input and the output. What if I change this to exponential form? I've got base b, logs are exponents, so the y is the exponent, b to the y equals x. Compare these. I switch the x and the y. I switch the input and the output. These are inverse functions. So this is another way that you could figure out what the log graph looks like. You could say the log graph is the inverse of the exponential graph. We just need to switch x and y. So instead of having the point 0, 1, we got the point 1, 0. Instead of having a y-intercept, we have an x-intercept, 1, 0. Instead of having a horizontal asymptote y equals 0, now we've got the x equals 0 vertical asymptote. If you remember inverse functions, they were reflected about the line y equals x. So if you picture the line y equals x and picture flip-flopping this graph across the y equals x line, this would flip down here. Got this vertical asymptote there, and then this flips around to be over there. Take this graph and reflect it across y equals x, and you'll get the graph that we just found. This graph right here. Okay. And whereas exponential growth is one of the fastest growing functions that we know, logarithmic graph, a log function, a log graph growing here, it does keep going up to infinity. It does keep going up forever here, but it goes really, really slowly. This one grows really quickly. This one grows really, really slowly. I mean, you look at this one here, we had to get all the way out to x is 8 just so we could get to y is 3. It grows really slowly. Okay, but the range is going to be all real numbers. It goes down to negative infinity up to infinity. Remember, inverse functions, since x and y are swapping, then that means that the domain and range are going to swap. So the domain here is all real numbers. So the range here is all real numbers. Here, for the exponential function, the range was 0 to infinity. So now the domain of a log function, we've seen this before. You can't take log of a negative. You can't take log of 0. The domain for log functions, the inputs for a log, have to all be positive numbers greater than 0, from 0 to infinity. Okay, and again, this is any base bigger than 1, so the most common one you'll see will be natural log of x, but that's pretty similar to just what we did a minute ago, the log base 2 of x graph. The base is not super important. It would affect some of these specific points. If this was natural log instead of base 2, this point would be up at 2.7. That point would be a little higher, a little higher. It would be a little bit steeper. If the base was 10, it would be a little bit steeper again, but actually the points would be over, so it'd actually be less steep. If this was natural log base e, we'd have to be at 2.7 to be 1. We'd have to be 2.7 squared to be 2. If this was base 10, we'd be all the way over at 10 just to have a y of 1. It would grow up really, really slowly, but it would still be the same general shape. The base just affects how steep the graph is. The basic features and the shape would still be the same. Okay, so then of course we're going to do what we did with every other type of graph. Now that we know the base graph, we can do some transformations. Okay, so log graphs, the key features are now a vertical asymptote and an x-intercept, instead of, again, the exponential had a y-intercept and a horizontal asymptote. So we've just flip-flopped x and y to have a different kind of asymptote and a different kind of intercept. So the vertical asymptote, okay? So you could think about it in terms of shifts. You could think about going left 4 and down 1, okay? So if normally we have x equals 0 right here as our vertical asymptote, we can think about going left 4 and then down 1. Well, making a vertical line go up and down doesn't change it. It's just the fact that we went left 4. So if you're at x equals 0, left 4, now you're going to be at x equals negative 4. What I probably recommend, though, because some of them are going to be a little bit harder to do with thinking about the shifts, again, for these, think about the x value. The reason that x plus 4 is a shift left 4 is because x plus 4 goes with x equals -4. Again, if you thought about zeros and factors, if x equals -4 is a zero, x plus 4 is a factor. If you set x plus 4 equal to 0 and solve it, you get x equals -4. I would probably do that kind of thinking for figuring out the vertical asymptote. The vertical asymptote is whenever what's inside the log function equals 0. Whatever x value makes the inside of the log equal 0. That's your vertical asymptote. Okay. The x-intercept, it's usually best just to solve for it algebraically. X-intercept, of course, is when y equals 0. So we would take log base 5 of x plus 4 minus 1 and set that equal to 0. So, of course, we can add the 1 over. The 1's outside the log, so we're free to move it over. But then the plus 4 is trapped inside the log, so I can't touch that 4 right now. So you might feel kind of stuck. Not sure what your next step is. Well, remember in this chapter, if you feel stuck, usually that means you have to change forms. So we've got 5 to the first is x plus 4. If you're stuck, it probably means you need to switch it between log and exponential, or vice versa. Okay, so we've got 5 equals x plus 4, which means that x equals 1. On the test, I'll probably have you write them as xy coordinates, so make sure that you know how to write that as a point. We already said that y is 0. Okay. So we can throw all of this on the graph here. So we've got the point 1, 0. Notice it's got the same x-intercept as the base graph, right? We moved this graph left 4 and down 1, but left 4 and down 1, we actually, those two combined together to actually make the x-intercept be the same. Kind of interesting, okay? And then our vertical asymptote, 1, 2, 3, 4 over there. This is still the same shape of a log graph, so the vertical asymptote is just going to be on the bottom end there. If you want to draw a whole dashed vertical line, you can, but it's just the bottom part where it approaches it. And then we just have our log graph shape, something like this. And that's the graph. Okay. On this one, for the vertical asymptote, again, I would just take a look at when does this equal 0? Because this one, having the negative on the x and the shift, does it go left 2 and then reflect? Does it reflect and left 2? How that's going to change what the x value you'd get would be. Just look at this and say, when does negative x plus 2 equal 0? And that would be x equals 2. So that's your vertical asymptote. Okay, so even though this plus 2 you're used to thinking of as a shift left 2, because of the negative on the x, the reflection, we actually end up at a positive 2 there. Okay? And so that'll be something important to note right here because of this negative on the x. So we have negative x's. Well, if you change x between positive and negative, that means we have to reflect about the y-axis. We'll have to make sure we remember that for the shape of the graph. All right, so we want to find our x-intercept. So f of x is y, of course, so we replace y with 0. Remember that natural log is base e, and so to solve this, there's nothing we can do right now. Everything's inside the log, so we might feel kind of stuck, so we're going to change forms. The base is e to the 0 equals negative x plus 2. So 1 equals, really I should say the opposite of x, plus 2. Subtract the 2, negative 1 is the opposite of x. That means we get x equals 1 again. Just a coincidence here, it's not always going to be 1, 0. It is 1, 0 for the base graph. And it just so happens that these graphs with multiple different transformations put those transformations together, and it actually brought the x-intercept back to 1, 0. But it will not always be 1, 0. You do have to actually set y equal to 0 and do the algebra, solve for it. Okay. So let's put this on the graph. So we've got an x-intercept here. Okay, and then we're reflecting about the y-axis. So normally the graph would go like this, but now it's going to go this direction. We will still have the vertical asymptote on the bottom half of the graph, But notice having the x-intercept and the asymptote kind of helps us on this one see that shape. We can see, well, hey, I'm not going to the right of the asymptote anymore. Now I'm going to the left side of the asymptote. So that's what that graph would look like. All right, so now I'm going to have you try some of these on your own here. I've got a few of these for you to try. So you're going to do log base 4 of x plus 1 there. And then on these down here, you're going to have some negatives out front. We haven't done one of those yet. So think about, we had a negative on the x reflecting about the y-axis. Make sure you remember what a negative out front does, what kind of reflection that's going to be. And you go ahead and try graphing those three functions. Go ahead and try number 3, number 4, and number 5 here. Notice we haven't really paid attention to the base. The fact that it was log base 5 here didn't matter too much. It was still that same general shape. So, log base 4, log base 3, when you do your algebra to find the x-intercept, you'll have to, have that number in your algebra. But otherwise, whether it's base 5, natural log, base 4, not going to affect things too much for us. Go ahead and give those problems a try. So we can check our answers here. So number 3 wasn't too bad. It was just a shift left 1 from our base graph. For number 4, that negative out front, we've got negative y's, and so we're reflecting about the x-axis. So instead of the asymptote being on the bottom part of the graph, the asymptote is on the top half of the graph. We just flip-flop the y's between negative and positive, reflected across the x-axis. Okay. And then for number 5, we reflected it both ways. We changed both the negative and changed both the x and the y between negative and positive. We reflected across both the x and the y axes. And so the shape gets all flip-flopped around. And it looks like what you see right there. Okay. If you ever weren't sure, of course, you could always try to find some more points as well, right? You could try to think of, what's another x that I could plug in there that would give me some nice values. So you can maybe think about something like, well, if I had x equals 8, then I'd be doing negative log base 3 of 1. Plus 1, because log of 1 is easy, right? Log any base of 1 is 0. And so it'd have 0 plus 1 would be 1. So that would be, giving you another nice point that you could have to kind of check, okay, at 8, the y is 1. And so that means it's going up on this side. You could always try to find the y-intercept as well, and then you would find the y-intercept is down here. So if you're ever not sure about these reflections, just try plugging in another x value or two, find another point or two to help you figure out that shape.